Okay, so in this video we're going to look at problems 5, 6, and 7. So number 5 states compute the derivative of w with respect to z of the function w equals the square root of 1 plus z times e to the z power. Well, in this problem, just to make a note of it, we're going to be using two rules. The first rule will be our chain rule that states that if you're taking the derivative with respect to x of f of u, where u is a function of x, then it's just f prime of u times u prime, right? In other words, take the derivative of your outer function multiplied by the derivative of your inner function. Now, for the product rule, if you take the derivative with respect to x of u times v, it's going to be u times v prime plus v times u prime. So you're going to see that these two rules are helpful to find the derivative of w with respect to z. So for our equation, w equals square root of 1 plus z e to the z power, you want to rewrite this using fractional exponents, right? So we're going to have, in parentheses, 1 plus z e to the z raised to the power of 1/2. So when we take the derivative with respect to z here, we're going to get that dw dz, or simply w prime, is going to equal to the following. Well, I'm going to bring the 1/2 down, so we're going to get 1/2 times 1 plus z e to the z power raised to the power of negative 1/2. Remember, we're going to have to subtract 1 from that exponent. So 1/2 minus 1 is negative 1/2, multiplied by the derivative of 1 plus z e to the z, since that's my inner function. Well, the derivative of 1 is 0, and now what I need to do is find the derivative of z e to the z. So if we find this derivative, I'm going to need to use the product rule. So I'm going to keep z, take the derivative of e to the z, which is just itself, plus take the keep e to the z, and I'll take the derivative of z. Well, your derivative of z is going to be 1, which is just going to be e to the z times 1, which is e to the z. So that will be our derivative, and of course we can definitely simplify this. Notice that I can rewrite this as follows. We're going to have dw over dz equals, let's see, what we can do is rewrite this as a fraction where our exponent will go down to the denominator. So we're going to have 1 over 2 times 1 plus z e to the z raised to the power of 1/2 times, now here, z e to the z plus e to the z, if I wanted to, I could have factored out an e to the z, so that will give me e to the z times z plus 1, and now I'll just multiply all this out. So writing this as a single fraction, we're going to get dw dz is going to equal to 1 times e to the z times z plus 1, which is simply going to be e to the z times z plus 1 over 2 times 1 plus z e to the z raised to the power of 1/2. And that's your final answer. And what I did was, just a little side note, this is my final answer in its simplified form. Alright, let's look at problem number 6. Number 6 states find the limit as theta approaches 0 of 3 sine of 4 theta over 5 theta. So one thing to make a note of is that I want to use our special limit. So note, if you have the limit as, let's say, instead of theta, let's use u. If I have u approaches 0 of sine of u over u, right? Once your angle, right, for sine is the same as whatever is in your denominator, then we know that this limit goes to 1. So what I want to do with our limit here, the given one, is first rewrite it using some limit laws, and then I'm going to do some algebra. So what we're going to have is the following. First of all, I can take the 3 over 5, our constant, and pull it outside of our limit. So we have 3 over 5 times the limit as theta approaches 0 of sine of 4 theta over theta. Well, if you notice, in this case, your argument for sine, meaning your angle, 4 theta, is not exactly the same as what's in the denominator, which is theta. So what we're going to need to do algebraically is just multiply the numerator and the denominator by 4, right? In other words, we're just multiplying it by 1, right? Since 4 over 4 is 1, so we're not really technically changing anything here. So when I do so, we're going to get the following. We'll have 3 over 5 times the limit as theta approaches 0. Oops. Now in my numerator, I'll have 4 times sine of 4 theta over theta times 4, which I can rewrite as 4 theta. Now lastly, in order for me to use my special limit, I can pull the 4 out. That's located in the numerator. So I'm going to have 3/5 times 4 times, so write it all out. What we're going to have is, oops, is 3/5 times 4 times the limit as theta approaches 0 of sine of 4 theta over 4 theta. Now since my argument or angle for sine matches my denominator, I know that this entire limit goes to 1. So we have 3/5 times 4 times 1. And you just multiply this all out. 3 times 4 times 1, that's going to be 12 divided by 5, and that's your final answer. 12 over 5. Now, I'm sorry about using pen. My markers are all pretty much done for, so I'm sorry about using a pen here. Okay, that's number 6. Now let's take a look at number 7. We could probably look at number 7 and 8 in this video. Okay, so for number 7, it states find the limit as x approaches 1 of x squared minus 4x plus 3 over x squared minus 1. So in this case, which I technically didn't do in the previous problem because I just looked at it and say, hey, we can use our special limit. In this case, we first want to directly substitute our 1 and see what happens. If I have an indeterminate form, then I need to sort of rewrite our limit first and try to simplify it and then compute the limit. So if we directly substitute 1, we're going to get 1 squared minus 4 times 1 minus 3 over 1 squared minus 1. So I'm directly substituting our 1 for all our x, and now I'm going to compute this. Well, 1 squared is 1. I'm going to have, sorry, it should have been a plus 3. We're going to have 1 squared, which is 1, minus 4 plus 3. So that's going to be 1 plus 3 is 4, minus 4 is 0 over 0. So since I have an indeterminate case, right, since this is an indeterminate, I know that I can rewrite my limit using one of our strategies that we discussed way back in the day while we were in class. Well, that strategy I can use is the factoring. So what I can do is factor the numerator and factor our denominator. So what we'll have is the following. We're going to have the limit as x approaches 1 of, well, the numerator, you can factor x squared minus 4x plus 3 as x minus 1 times x minus 3. Negative 1 times negative 3 will give me a positive 3. And if I take negative 1 times negative 3, it does equal to negative. If I take negative 1 plus negative 3, it does equal to negative 4. Divided by x squared minus 1, that's a difference of two perfect squares. So I have x minus 1 times x plus 1. Now if you notice, I have a binomial factor that they both numerator and denominator has in common. That's x minus 1. So I can cancel that out as long as x is not equal to 1. Right, so as long as x is not equal to 1, I can cancel it out, and we'll have the following. We'll have the limit as x approaches 1 of x minus 3 over x plus 1. Well, we can directly substitute now. We're going to have 1 minus 3 over 1 plus 1. Well, 1 minus 3 is negative 2. 1 plus 1 is 2, so negative 2 over 2 is going to be 1. So the limit as x approaches 1 of x squared minus 4x plus 3 divided by x squared minus 1 is equal to 1. Alright, and finally in number 8, it states find the limit as x approaches infinity of 6x squared plus 100 over 7x squared minus 100. So when you're trying to find the limit as x approaches infinity, we can do two things. Well, one, you can divide each term by the highest power, and then you can use this fact. If you have the limit as x approaches infinity of some constant c over x to the n power, then you know that this is always going to equal to 0, since c is going to be just a single puny number, whereas the denominator is going to grow extremely large. So with that being said, I'm going to divide each term, 6x squared plus 100 over 7x squared minus 100 by the highest power, which is x squared, simplify, and then use my fact. So we have the following. We have the limit as x approaches infinity of, well, in the numerator, you'll have 6x squared over x squared plus 100 over x squared divided by 7x squared over x squared minus 100 over x squared. Now I'm going to simplify this, and then we will be able to compute the limit. So we're going to have the limit as x approaches infinity. Well, 6x squared over x squared, your x squareds will cancel, so it's going to be 6 plus 100 over x squared. I can't do anything with that, so I'm going to just rewrite it. 7x squared over x squared, that's going to be 7 minus 100 over x squared. Now I'm going to compute the limit as x approaches infinity, and I'll get my answer. So if I take the limit as x approaches infinity of every single term, well, the limit as x approaches infinity of 6 is going to be 6. The limit as x approaches infinity of 100 over x squared, if I use this fact, right, you're going to have 100 over a very large number, that's going to be 0. Divided by, take the limit as x approaches infinity of 7, you're going to have 7. Take the limit as x approaches infinity of 100 over x squared, that's going to be 0, so I have 7 minus 0, and now I just simplify. 6 plus 0 is 0, 6 plus 0 is 6, my bad, divided by 7 minus 0, which is 7. So your final answer is going to be 6 over 7. Now lastly, another way that you can compute this limit, is that you could compare the highest power of the numerator and your denominator. So that's just an alternate way. If you looked at this limit, if you compared your highest power in the numerator and denominator is both the same, so you're looking at the limit as x approaches infinity of 6x squared over 7x squared, and you see that you'll still get the same answer, 6 over 7. Now let's say that if the denominator was a 5, right, so 6x squared over 7x to the 5th, then this special fact would come into handy where that limit will go to 0. That's pretty much it for problems 5, 6, 7, and 8. On to the next video.